Well, let's start off with the fact that your book is a quotation from Carl Sagan, one that I have to admit I used to use myself a great deal as well in stand up, the how to make an apple pie from scratch. What were your first inspiration? Because you're too young to have seen Carl Sagan's Cosmos on the first time round, whereas I saw it when I was about 11 years old.
Yeah, I think the earliest thing that I can remember probably were watching Horizon documentaries on the BBC. And then there was one particular book that really made an impact on me when I was a teenager called The Magic Furnace. I don't know if you've read it, but it's by Marcus Chown, who's a very prolific science writer. And it was basically about the search for the origin of atoms and how we figured out that atoms were made inside stars and the Big Bang. And that was, I remember, I think in my year when I was applying for university, you had to sort of write down in your UCAS application, you know, what were the things you were sort of reading around the subject, and that was one of the things that I remember mentioning there. But it's kind of been in my head ever since. And I guess what I'd want to do with this book was it was almost sort of taking what Marcus had done with that book and taking it a lot further. He sort of talks about where do atoms come from, but this book goes further and where do the things that atoms are made from come from and how far back can we go. But that's probably the thing that made the biggest impact on me that I can think of when I was a kid. Yeah.
So did you have, in terms of your science teaching, were the people who were inspirational? Was it friends, family? Or was it just something that almost feels, I know it's very dangerous to say innate, because we know nature, nurture, the clash of all of these things. But, you know, what was that influence?
Well, I think it was a mix. My parents both, my mum did chemistry at university, and neither of them became scientists. My dad started off doing physics and then lapsed and became a historian and philosophy of science student, and then went off and worked for British Telecom. So they both had a sort of scientific background. So I guess I was always encouraged to have a sort of interest in science. But actually, I mean, it's sort of a cliche, but I had a few really great physics teachers at school, but I also had some ones that were not so great. So I think it was a kind of mix. I mean, there was a couple of teachers who really had a big influence on me, but then also I think reading around the subject was a big part of it. Because actually, I shouldn't really say this, but I think I do say this in the book, that physics at school can be a bit sort of sterile in some ways, particularly the labs. You remember you doing these experiments where you're wiring up a circuit over and over again, or kind of timing a pendulum swing. And I that's all, you know, you need to know all those basics to kind of get into, you know, to actually get into the subject. But it was all the big ideas like, you know, the Big Bang and cosmology and particle physics that kind of drew me in. But you don't get very much of that at school. You only get that really by kind of reading around. So I think a lot of the kind of impetus came from speaking to my dad and my mum about science and kind of reading books, watching TV. And then eventually at the very end, I think when I sort of my school career, you do a little bit of particle physics. And I was like, oh, this is now getting to the exciting stuff. But of course, then you get to university and it's back to pendulums and electric circuits again, because you've got to start from the basics.
Yeah, I was interested. I remember the first time that I met Faye Dowker, who's based at Imperial, and you know, the general relativity doesn't come in till I think it's the fourth year in Imperial, which is her most exciting moment. Before she does that lecture, she's properly hyped up as if she was about to go and do Wembley Arena, and then goes on and delivers that. And you can see all of the students are so excited that they finally get to really meet Einstein at this point. But it's interesting to me, which is, I was talking to a science teacher a while ago who said one of the problems he feels with science education is that really the science education is to find out who's going to be a scientist, and that all the other people will drift off in a way that you don't see so much with English or history. You know, it's not expected. And I wondered how you feel about that idea that we need to have some form of science education which says, this is not to say that you're going to end up working at the Large Hadron Collider. This is just to connect you to some of the ideas of the universe, some of the things that are around you, some of the magnificent ideas.
Yeah, I think that's right. I think it was Ken Robinson who did a very, very, very heavily viewed TED talk about this idea that the education system sort of assumes that the end result is you're a university professor. And actually you kind of miss out of not just, you know, even within science, I guess, as you're saying, but more broadly, all these other skills that and sort of interests you should be stimulating. But yeah, I think that's right. And I think that's one of the reasons, one of the important roles I think that sort of public engagement has from sort of areas like particle physics and cosmology is there's a lot of evidence that people who get into science or have an interest, that they may not become scientists, but they have a sort of lifelong interest in science. It comes through those kind of big, you know, those big ideas, and that has a really important role. And you kind of do need to give, I think, people more of a flavour of that when they're younger. And at the moment, I think it mostly comes in through media and through other things, and not so much. Although I think, I mean, I'm now pretty out of date into my school education, was a long time ago now. I think there is a move to put more of that sort of like quantum particle physics-y kind of cosmology stuff in a bit earlier to kind of liven the subject up. Because you don't just want to spend 7 years doing, kind of fluids and Newton's laws and stuff. As important and interesting as that all is, you do need some of that sort of magic stardust, I think, to spur people along. And also, even as you say, if they don't become scientists, they've got a better overview of what the subject's about, rather than the sort of science as it was 100 or more years ago.
Yeah, I think that's. I mean, what for you? If there was one idea that you would think, because I know a lot of teachers I speak to just go, "Oh my God, they've added more equations to the curriculum. Less story, more, and it's not actually about understanding the equation; it's about remembering the equation." So, if there was one idea that you think this is what I would definitely have in science education, this is the one that it's going to be the fantastic whiz bang excitement of. There's no way you're going to leave the universe alone. Now I've told you this.
Ooh, that's a tricky one. I mean, I think maybe I'll pick on. So this is maybe a bit ambitious. I don't know if it is, but I think one of the things that people is not widely understood about our understanding of what the world is made from is that we have this subject, particle physics, and that sort of suggests that we think that the universe is made of little spheres, little particles that kind of join together to make atoms, and that is really far from the modern view of what the world is made from. And actually, particles aren't thought of as the fundamental building blocks of the universe anymore. And building blocks itself is a problematic term, actually. I mean, the basic ingredients we think are these really ethereal, otherworldly objects called quantum fields, which are these kind of ever-present, invisible, sort of intangible objects that are all around us. And the particles like electrons and quarks that make up atoms in modern particle physics are thought of as little vibrations, little kind of waves, basically moving around in these sort of invisible fluid-like things that are everywhere. And I think that idea is really quite beguiling. It's kind of counterintuitive, but also really exciting. But it's not something that, even as a physics student, you really get to grips with until quite late on in your education. And I think in a lot of the popular discussions around particle physics I don't think it's emphasized enough that actually this old-fashioned kind of little balls moving around in a vacuum view of the world is not what the world is like. It doesn't appear to be that way. I think that's a really magical idea, and you can kind of, if you can get some of that across, and I mean the mathematics of quantum field theory is way too advanced for even most undergraduate courses, but I think if you get some of that excitement, you get some of that idea across, I think that's a really powerful idea that could excite people.
I love that line. I think it's Niels Bohr who said that all of reality is made from things that ultimately aren't real, which is, that's and that's going to spark your mind, I think. So when you started writing this book, and as you said, I mean, what's interesting is when we go back to Marcus Chown's book is probably over 30 years old now. So it's one of his earlier books. I mean, there's been such changes in understanding, that realization about the Higgs particle and the Higgs field and all of. So that's one of the things that I think I find very exciting, is that the book that you're writing is filled with things that were not. This was not a universe that existed in scientific imagination, in human imagination. This is a new picture of the universe.
Yeah, we've come a long way. I think the book came out in like 1996 or something. So it's sort of been like 25 years or something like that. And it's true, we've learned a lot. And in other ways we haven't. It's this kind of, if you think about particle physics, we have this very, very successful, frustratingly successful theory called the Standard Model of Particle Physics, which was put together in its current form in the 1970s. And has we've basically, the story of fundamental physics since then, at least in particle physics, has been basically to confirm the predictions of the Standard Model. So the force particles that were predicted by Weinberg and others in the 70s were discovered in the 80s, and various different quarks were discovered in the 90s. And then the end of the story was the discovery of the Higgs just about 10 years ago at the LHC. So we had this theory, and the story of particle physics has been this amazing story of theory predicting the existence of things that had never been seen before, and then them being found. So in that sense, we've learned a lot. We didn't know then. We kind of had this idea, and now it's all been confirmed, and we can talk about this story of what matter is made from, what happened in the very first moments of the Big Bang with a lot more confidence than we could maybe 20 years ago. But at the same time, in some ways, we're still in the same paradigm. We haven't moved beyond the ideas that were kind of invented or discovered in the almost 50 years ago now. And that's sort of both, I guess it's a triumph of the theory that was put together, but at the same time it's quite frustrating, because we know that there are big problems with our current understanding of the universe, big mysteries that we can't solve, like what dark matter is, why there's stuff in the universe at all. And the Standard Model has no answers for these questions. And we've been at the LHC the last 10 years sort of banging away, trying to find some chink in the Standard Model's armor where it starts to come apart. And so far, at least, we've not seen anything that's totally confirmed. Although the thing that's really, and I mentioned this right at the end of the book, and the thing that my experiment has been working on for the last few years, there's these interesting anomalies that we're starting to see, which we hope might be the first step to a new paradigm, a new way of thinking about fundamental physics. But it's kind of, we're in that uncertain stage where we don't yet know if these things are real, whether they're going to pan out, or whether we're going to find that they sort of evaporate and we're back with the theory from the 1970s again and feeling frustrated. So and we've learned a lot, we've come a long way, but at the same time, we're still waiting for that big next breakthrough that really would take the story to the next step, I think.
Well, explain to people what the Large Hadron Collider, what it allows you to see, what it allows you to test.
Yeah. I mean, the LHC, well, it's a hugely, you can use it for a huge range of different things, which is kind of strange in a way, because it only does one thing, basically, which is it smashes protons together at the highest energies we've ever been able to create. But because of the wonder of quantum mechanics, when you smash two protons together, you can't predict in advance what's going to happen. There is basically an infinite number of possibilities in terms of what particles could get created. So in very basic terms, what the LHC does is it makes particles out of energy. The reason you accelerate protons around the ring is you give them lots of kinetic energy, they collide, and that kinetic energy is used to make new particles that you then study. So in that sense, we're studying, what are the basic ingredients of the universe? And these particles are things that do not exist ordinarily in the world. They're, take the Higgs boson, for example. These Higgs bosons haven't existed in the universe in large numbers since about a trillionth of a second after the Big Bang, because they're very, very massive. They require large amounts of energy to make, and as soon as you make one, in like 10 to the minus 25 seconds or something, they decay into other things. So another way of thinking about the LHC, it's sort of like a time machine. You're kind of, by creating these incredible energy densities and temperatures, you're recreating in microcosm the conditions that existed in the very, very, very first tiny fractions of a second after the Big Bang. And that's where a lot of the big questions in fundamental physics live. There's a lot of mysteries I talk in the book about the first trillionth of a second. And we can basically tell this amazing story that goes from now back to about a trillionth of a second after the Big Bang. And that's where things start to get a bit shaky, and we don't really know what happened before that. And the LHC is kind of pushing us further into that very first fraction of a second. But in terms of, people are looking for, dark matter particles being created in these collisions. Particularly what I look at is me and my colleagues study particles called bottom quarks, which are quarks are the things that make up the nucleus of ordinary atoms. And there are two of them in the two of the ordinary types of quark, but there's four other exotic ones. And the bottom quark is one of these exotic types. And we study these quarks in really, really a high level of detail, because they're very sensitive to the existence of other quantum fields, other force fields that might be hanging around in the vacuum that we haven't seen yet. So basically what we're trying to do is catch bottom quarks behaving in a way that the Standard Model can't explain, and that could be then a clue to what might come next. So, but yeah, and the LHC is amazing. You can do all kinds of things with it, but that's particularly what I'm interested in, these bottom quarks.
See, I'm fascinated by that idea. When you talk about the first trillionth of a second, and I remember talking to Carlos Frank from Durham University, he said the problem is that we think that's time. But actually, when you go back that far, and I presume this is part of the whole problem of trying to glue together, this how can we get gravity and quantum theory to work together? Which is, he says, well, actually, it's not really. It's in his mind, it may well not be a trillionth of a second, because we're moving into a time where is space the whole topsy-turvy kind of black hole ideas as well. So is that part of the problem, is when we see that 10 to the minus 38 or whatever it is sometimes quoted, and that actually we think, oh, so that's just that little bit of time. And he goes, well, it might not actually be time. Does that make sense or not?
Yeah, I mean, I maybe the way I'd look at it is that if you say we know the story back to a trillionth of a second after the Big Bang, you might think, oh, we've got it all sorted then. I mean, that's just, a little detail. But as you go, every tiny little sliver of time you go further back beyond that, more and more stuff potentially happens. So you crowd a huge amount of very important events into a very short space of time. So, basically, if you go from the moment of the Big Bang to about 5 minutes after the Big Bang, by that point you've gone from something which we don't really know what happened at the beginning to hydrogen, helium, and lithium, and you start to get things that are recognizable. And there's a lot of processes that happened in that first 5 minutes that created all of that stuff. And so, yeah, I mean, in terms of, I mean, time as we understand it probably wouldn't really have very much meaning, because I think, well, I mean, I'm not, this is getting way out of my comfort zone because I'm an external theorist, but like, you know, this idea that time is really an expression of kind of entropy, that the reason we perceive a direction for time is that, well, maybe I take it another way. If you go down to particle physics level and you look at basically everything, the only thing that happens down at the fundamental level is 2 or 3 particles bang into each other and they bounce off. And you can run those processes forwards and backwards and they look basically the same, and there's no preferred direction of time. But time seems to come about because if you have lots of atoms and lots of particles moving around, let's say, for example, you've got a container, on one side you've got, you know, blue particles for the sake of argument, the other side you've got red, and they're separated. As you lift up that barrier, they all bounce around and they mix together. And in each one of those individual bouncing around processes is reversible. But at the end, you end up with a purple container of mixed, you know, red and blue. And you can wait the age of the universe, and you'll never find, it will never go back to being blue on one side and red on the other again. So time seems to is an emergent thing that comes out of many objects interacting in a way. So I guess in that sense, that kind of time probably doesn't really exist during the Big Bang, because, you know, the world is completely unrecognizable. But yeah, I mean, so time is in some sense misleading, because it sort of sounds, this trillionth of a second sounds like we're almost there, but actually every step you take further back gets harder and harder, and the energies you need get higher and higher and higher and higher. So you kind of, it's this kind of like, you kind of approach zero, but every time you get nearer, it's the hill you're climbing gets steeper, which is why you keep building bigger and bigger machines and bigger telescopes to try to kind of peer back further and further.
What have you found the most difficult idea for you to deal with instinctually? Because I presume that's one of the battles that you have all the time, is that you have to sometimes usurp the instincts that you're brought up in for the scale of the world that we interact with.
I think, well, so this is this isn't really a scientific concept, but as an experimentalist, the trick to being, well, the kind of the key quality an experimental physicist needs is to doubt everything. So you have to, when you get a result in an experiment, for example, if let's say, you know, at the LHC, we've been looking for new particles, new physics for the last 10 years. So when you see like a new bump in a graph that could be, you know, the sign of a new particle, there's a huge amount of like emotional kind of drive to believe that thing is real, because you really want to have found something new. And that is really dangerous as a scientist, because, you know, of course we want to discover new stuff, but if we're kind of we're willfully kind of trying to find it in the data, you can easily fool yourselves. So I think that's one of the hardest things intellectually to kind of overcome as a scientist, is to actually say, okay, as much as I would like to, you know, discover something really exciting and new, I've got, every time I come up against a new problem or a new bit of data that could be telling me something, I have to start by, you know, doubting it as much as I can, and trying to scrutinize it, to find all the places where it could be wrong, where we could have made a mistake, where, you know, we could be being misled. And that is I think one of the struggles. And theoretical physicists, I think, to some extent a bit more free. They can kind of speculate wildly and come up with ideas which, you know, it's interesting that the attitude, these anomalies that I mentioned that we've been seeing in the last few years at the LHC, the theorists tend to be much more gung-ho. They're kind of like, yeah, this is really exciting, we're on the brink of something new. Whereas the experimentalists are like, kind of, hang on guys, let's cool it down. That these experiments are really complicated. There's plenty of places there could be a mistake still. So I think that's that's something I struggle with all the time. It's kind of, you know, keep calm, just kind of scrutinize. And at the end, when you finally get the result, okay, we've done everything we can. Now we can sort of say with some confidence that what we're seeing is real. So that I think is a hard thing.
Did you have a system in terms of when you were writing the book, which is a very approachable book, but at the same time is, of course, dealing with ideas that some people may never have read about and are not part of the kind of common culture? What was your process? Did you have various readers who would go, Harry, you've forgotten that people don't know what these were, and so you need to go back and you need to explain this and you need to explain that? Was there a kind of a system that you put in place?
I mean, I had like friends and family who read everything I've written, and none of them are physicists, so that they were a very useful sense check. I think one of the advantages, the way the book is structured, is it literally starts with an apple pie and eventually ends up at quantum gravity somewhere at the far end. And because of the way it kind of builds up the knowledge, I think hopefully the idea is that you're kind of, with each chapter, you're adding a new layer on top of what you got before. So you kind of can trace the ideas back. But I suppose the other thing is the book is I'd say there's, as well as the scientific ideas, there's also a lot of storytelling in the book. So there's kind of, I describe a lot of the, particularly in the earlier science, we're talking about the origins of chemistry and atomic physics, talking about the characters from history, people who were involved in the discoveries. But also quite a lot of visits that I went on when I was researching the book. I was really lucky to go to some really amazing places, and it's amazing actually when you approach scientists. I was quite nervous when I was writing the book of kind of emailing some eminent astrophysicist to say, can I come and look at your telescope? And then people are amazingly receptive and then sort of say, oh, of course, yeah, of course. So I ended up doing things like spent a night on top of this mountain in New Mexico with some astronomers, which was really, really great fun. So I tried to kind of mix the sort of hard science with some more kind of descriptive storytelling. So it's kind of, the book itself is a kind of journey of discovery to an extent. But in terms of kind of getting the ideas across, I think it's partly also the way I think, which is that in order to understand something, I really have to kind of take it down to its like simplest elements. And I think because of that, I think that's potentially why I've got something, that gives me a kind of, that's a useful starting point for explaining scientific ideas, because I can kind of remember when I was first coming against these ideas, well, how did I break this problem down to a point where I could get my head around it? And if you do that, actually, most scientific ideas, although there are some that are very hard, the thing that makes them confusing is you're kind of building on a whole body of assumed knowledge. And that's where people get lost. Actually, any individual idea is quite often not that hard, but you lose people when you start using unfamiliar terminology or jargon. So as long as you build that up from the basic level and treat people as, you know your audience are intelligent, but they're not necessarily knowledgeable. And that's, I think, the thing to remember.
There's the thing Richard Feynman talked about. I can't remember which particular idea it was, where he was asked to write an hour-long lecture about it, and he just kept writing it, and he realised he couldn't get it into an hour. And then his realisation was, if we can't get it into an hour-long lecture, it means that we don't really understand it. And I wondered, was there any point when you were writing this book where, what was the hardest thing to break down, to create the stories around it, to get that sense that you are able to deliver that knowledge?
Yeah. Well, there was one idea, and this is an idea that I myself as a physicist struggled with a lot. So this is going to get way out there. But in the book, I talk about these really weird objects called sphalerons. So sphalerons they're not particles. They're basically things that emerge in quantum field theory, in our kind of theory of what the universe is made from. And I'm not sure even now I can really explain to you properly what they are, but the reason they're interesting is these things called sphalerons, we think they existed about a trillionth of a second after the Big Bang, and they might have been the objects that allowed matter to be created over antimatter. So we have this big problem in particle physics, which is every time we do an experiment at the LHC, you bang particles together, you make particles, and you also make antiparticles, their sort of mirror image. And every experiment we've done so far, you always make an equal number of particles and antiparticles. And that suggests that in the Big Bang, when you have the creation of matter, you should also create antimatter. Had that happened, the matter and antimatter created in the first few fractions of a second would have met up with each other, annihilated, and you end up with an empty universe with nothing in it apart from a few lonely photons coasting through the infinite blackness. And we think that so one of the big questions in particle, the big problems in fundamental physics, is how did matter win out over antimatter? And these sphalerons things are thought of possibly being part of the solution to that problem. So I remember going to speak to the theorist. He's a very eminent fellow Royal Society at Cambridge who came up with the idea of sphalerons in the kind of on pen and paper back in I think it was the 1980s. And he very gamely, I remember I spent my whole morning with him. He was really, really generous with his time, writing equations on blackboards, drawing diagrams. And it was one of those things where you're kind of listening to him. And as you're listening, I think I'm just hanging on by my fingertips. I just about get this. And then as soon as I walked out the room, it just kind of evaporated. It kind of, so trying to get that across, I think I probably, in the end, he was very generous when he read the passage back. I think I really missed out pretty much everything he said apart from the very, very simplest ideas. So that was one of the struggles. But I do come off, often as a scientist, you come up with, particularly as an experimentalist, coming up against ideas that are really unfamiliar to you. And actually to really understand, you're going to have to spend a year probably doing an advanced course on these sorts of things. But it's finding the kind of, what's the important thing about this idea and what's the essence of it. And in the case of these sphalerons, the way I think I eventually explained it is, if an ordinary particle like an electron is a little ripple in a quantum field, so there's this thing called the electron field, and an electron is a ripple in the electron field. Well, a sphaleron is sort of like a load of different quantum fields all moving together, a bit like kind of, I don't know, it's almost like having multiple fluids moving in motion together. That's sort of about as close as I could get. And the theorist who I spoke to said, yeah, that's not totally wrong. I think you get away with that.
Not totally wrong is a victory. That's definitely a victory. The what for you, the final question really, which is, you're working at the LHC, which is such a remarkable, when you look at the structure of that, every different level of the building of that, and you think about the time that was required from someone coming up with an idea to then actually being able to, with technology, test it. And I think about things like, also gravitational waves, the recent kind of discovery, the actual measurement of those. What for you now is the next thing where you go, well, all we need now is just this enormous budget to create this incredible, those things where we've got the idea, but we now need to build the machine that's going to test it. What for you is the most exciting possibility in that world?
Well, so I think what I would like to see happen, and this is on such a long time scale, I don't even know how much of this I would see in my own career, and I'm not that old yet, there's a machine being planned, the successor to the LHC, which is called the Future Circular Collider, it sort of makes the LHC look like a bit like a little toy. It's a 100-kilometer circumference particle accelerator, again at CERN. It's basically the biggest machine you can fit in the Geneva Basin. So it kind of runs between the Jura Mountains on one side and the Alps on the other. It goes under Lake Geneva and around the entire city, essentially. So this machine would take us to a whole new regime. It's going to go sort of an order of magnitude higher in energy than the LHC. And particularly from my point of view, the thing that's really, well, there's two really persuasive reasons for doing this. One is to do with the Higgs boson. So the LHC found the Higgs boson, but the Higgs boson is a really troublesome particle to understand. According to our current understanding of particle physics, such an object shouldn't really be possible. It shouldn't really exist. And one of the big questions that we haven't got an answer to, and the LHC probably can't answer, is the Higgs boson really a fundamental particle, or is it made of something else? Is it actually, if you zoom in close enough on the Higgs, will we discover that there's something else inside it? Because if that's true, that could solve a lot of these weird problems with the Higgs. And this giant machine will basically be like an enormous microscope that can zoom in on the Higgs at an incredible level of detail and tell us, is this thing really as weird as we think it is, or is there something else going on? But the other reason that I think is potentially exciting is these anomalies that we're seeing at the LHC at the moment. What they're hinting at is the existence of new particles, so that some kind of new particle, but these particles could well be too heavy for the LHC to create. So it could be that these things are kind of just out of reach at the moment. So if these anomalies are confirmed, and it's looking like they might be, although it's still a bit too early to say, that could be telling us that at the next machine, there's a new set of force fields, a new set of particles that we could well discover. And that machine, we are pretty sure, would be guaranteed to be able to create them. So those are the two really persuasive reasons. I mean, I think it's going to be, CERN just put out their kind of aspirations for building this machine last year, but now it's this long process of R&D. And I think in the sort of most optimistic scenarios, it doesn't come online until the 2040s and it runs till the 2070s. So, I mean, by 2070, I hope at least I've been able to retire. So yeah, I have to say, I find it amazing thinking back to people who worked. I think the first conversations about the LHC happened in the late 70s, in sort of 1976, something like that. And to imagine a project, in a lot of cases, there's people who you're not going to live to see the thing realize. It didn't come online until 2009. So you're talking, more than 30 years. And science seems to be increasingly going that way, particularly in cosmology and particle physics, these really long timescales. And I think it's amazing actually that you can coordinate people to work on something that they'll never see the fruit of. It's a bit like building cathedrals in the sort of Middle Ages, where you build a bit more of the cathedral every generation, but you know that it's not going to be finished for a century or more. And that's sort of the way physics is going. I think one of the things to talk about actually in the book is that in the 90s, when I was reading popular science, there was this sense that physics was hurtling towards a dramatic climax, that there'd been this incredible period of discovery and that we were going to get a theory of everything and it was all going to be wrapped up with a bow. And what we've realized actually is that the problems are much harder and longer term than we realize, both on the experimental side and the theoretical side. And that's that's the mindset I think we need to have if we're going to make progress, that we add a little bit more to the puzzle, as much as we can as we go. But the long-term vision is you have to keep going for decades if you really want to get somewhere in the end.
Yeah, I remember that's always a line I always used to use in presentations, which was, none of us are going to live long enough to hear the words, well, that's science finished then, isn't it? Harry, your book is wonderful and is a really great journey into us trying to understand what everything is made of and those structures. And it's so thank you very much for your time.
Thanks for having me. Love to talk to you.